In this lesson, we're going to finish up looking at the atom, nucleus, and radioactivity. We're going to start by looking at some of the uses of artificial radiography. Then we're going to have a look at Niels Bohr's contribution to how we interpret the atom. Then we're going to have a look in a little bit closer detail at atomic mass, and in particular, we're going to introduce a new unit, the mole. After that, I've got some questions for you guys to try, and then we're going to finish with kind of a bonus mission. So we've already gone into detail about how the Geiger-Muller tube works in detecting ionizing radiation. We're going to, as a bonus, have a look at the solid-state detector. Now, I say bonus because if you're fine with the Geiger-Muller tube, that's grand, but just for the sake of being comprehensive and thorough, we're going to have a look at that too. Okay, so before we look at the uses of radiography, just to be clear on the word artificial here, most of the isotopes we use are artificially made. We do that by taking a stable isotope and literally bombarding it with neutrons. We're going to look at how that works in a little bit more detail in the next chapter, but just to be aware that most of the isotopes we use are artificially produced by this neutron bombardment. Okay, so let's have a look at our first use, which is radiocarbon dating. You might have heard about this already. Now, this first image here of this kind of dinosaur fossil, radiocarbon dating is used to tell how old an artifact is. So if you're given a fossil or archaeological artifact, you can use radiocarbon dating to determine its approximate age. Now, this first picture here of this dinosaur, radiocarbon dating probably wouldn't be much good here, and by the end I'm hoping you'll be able to see why. But radiocarbon dating can help us to figure out how old a more recent biological artifact is. And I say recent, I'm talking the last kind of 50, 60,000 years. And biological meaning that it was alive at some point or was made from materials that were alive. So how exactly does it work? Well, in the atmosphere around us right now, there's a mix of carbon-12 and carbon-14. The carbon-14 is formed in the atmosphere when nitrogen is bombarded with cosmic radiation to give us carbon-14. But the thing is, it's kind of a set amount, and we know the ratio of carbon-14 to carbon-12. You don't need to worry too much about the mechanics, but just that there's a set kind of ratio in the atmosphere. And as long as an organism is living, it's exchanging carbon with the atmosphere all the time, either by photosynthesis, where plants take carbon dioxide to make sugars, or when we eat plants, or when we respire, or when plants respire, when they burn some of those carbohydrates to release energy. So the key here is the carbon is kind of constantly moving around. So as long as an organism is alive, the ratio of carbon-12 to carbon-14 in its tissues will be the same as the ratio in the atmosphere. But once that organism dies, it's no longer exchanging carbon with the atmosphere. It's just the carbon that's locked in to the organism itself. And the carbon-14 that's kind of locked in there will continue to degrade. And because we know the half-life of carbon-14, if we have a look at the relative amounts of carbon-12 to carbon-14, we can figure out how many half-lives have passed. And by doing that, we can then figure out how old the organism was. Because carbon has a half-life of about 5,700 years, it's useful for figuring out the age of relatively recent artifacts. Anything past 50,000 years, and there isn't usually enough carbon-14 left to give you an accurate reading. For that, you'd need an isotope with a longer half-life. So by choosing a radioisotope with different half-lives, we can set kind of the unit of the clock for the thing that we're trying to figure out the age for. To be honest, I got a little carried away with how much information on radiocarbon dating you actually need to know. You just need to know that it can be used to date different artifacts. But in any case, it's bonus knowledge for you. Okay, so our next use of artificial radiography is in smoke detectors. So if you remember, alpha radiation is very ionizing, but also very short range. So if you set up two electrodes and you have a alpha source in between them that ionizes the air in between them, allowing current to flow, then under normal circumstances the current will flow. But as soon as there's a fire, which kicks up a lot of smoke and small particles, they're going to block the flow of ions because the alpha can't penetrate through the smoke to ionize the air, so the current can no longer flow. And by detecting that break in the current, you can sound the alarm. Next use is for sterilizing food. So bombarding some food with radiation, you can kill the bacteria, fungi, any sort of parasites that may be lurking around in there. Now, the food itself is not radioactive. It's just been irradiated in that it's been kind of bathed in radiation to kill the pathogens that might be on it, so anything that causes diseases. The same technique can be used to sterilize medical supplies like surgical equipment. We can also use artificial radiography in a medical context to diagnose patients. That means to find out kind of what's wrong. So if you suspect somebody has a tumor or a clot, you can inject them with a radioactive isotope. Now, it has to be sufficiently penetrating to escape their body, so alpha wouldn't really be much good here. And it's usually kind of a gamma source. So it'll also have to have a relatively short half-life, both so that it'll be radioactive enough for you to detect it, and also so that it doesn't linger in the patient's system and cause them any problems. But you can use it when it circulates, so you can see if there's any blockages or how the fluid moves. We can also use it for medical treatment. So in addition to kind of finding out what's wrong with somebody, let's imagine cancer as an example. Cancer is made up of your own body cells that have kind of gone haywire and they're reproducing out of control. But they're more susceptible to radiation than your normal cells. So if you bombard a cancer tumor with radiation, you can reduce its growth and hopefully destroy it. Now, unfortunately, you'll still cause kind of collateral damage amongst your own cells, but if you position different sources in different directions, you can concentrate all the radiation on the target, and that way the nearby cells hopefully won't get as much as the target. In a similar approach to how we use radioactive isotopes as a medical tracer, you can also use them to detect kind of leaks in large chemical plants or water treatment facilities. There's one. So usually by using a gamma source, if you introduce it into whatever you're testing to see if it leaked, then you can look in the surrounding area, and whenever you got a high concentration of gamma waves, that's probably more likely caused by a leak from your radioactive source. So you can trace it back and figure out where it was coming from and plug it. Finally, artificial radiography has a plethora of uses in industry as well. So here's just two examples. The manufacture of aluminium foil, you can use a beta source to detect when the foil is too thick or too thin. You can use that to feedback to control how it's made. And it can also be used to detect when a hopper is full. So a hopper is like a big kind of tub thing. So if it's full of coal or grain or ore or products, so you can see when it's full by having a source and detector on either side. Next, we're going to have a look at Niels Bohr's contribution to our knowledge of the structure of the atom. So we refer to the way we look at the atom now as the Bohr-Rutherford model, and we've already explained Rutherford's contribution, but Niels Bohr also made a massive contribution to science. It's because of him that we know how the electrons behave in the way they do, and how they fit into our current understanding of the structure of the atom. Let's start by considering what happens when you heat something up, in particular a solid or a liquid. So if you heat something, it'll start to give out infrared radiation. And if you keep heating it and heating it and heating it, eventually it'll start to glow, and it will start to glow red. Now this corresponds to a certain temperature. It'll start to glow red at about 600 degrees Kelvin. If you keep heating it, eventually it will start to glow orange hot. That's about 1000 degrees Kelvin. And if you keep heating it and keep heating it and keep heating it, eventually you'll give out white, it'll go white hot, giving out white light. That's about 1400 degrees Kelvin. If we were to take this light that was given out by this heated object, and run it through a prism or a diffraction grating to separate out the colours, we'd see that we've actually got the full spectrum represented. All the colours are there. Now this will be regardless of which material you heat it up, it's just to be heated up sufficiently. So that's the case for a solid or a liquid. But something much more interesting happens if you heat up a gas. So if you take a gas of a particular element and heat it up, it will also give out light. But if we take this light and run it through a prism or a diffraction grating again, this time we don't have the full spectrum of light represented. We've only got particular colours. So we'll see them separated out in a line spectrum, and we'll see that there are particular colours represented by particular elements. So we can actually use this to identify samples of gas if we don't know what they are, because each gas will give out wavelengths of light particular to itself. So for example, the sodium street lights that we're kind of also familiar with, when you look out at night and it's kind of orange, that's because we use sodium street lights, sodium vapor. Okay, so why does this happen? Bohr's model explained this behavior. So the idea is that electrons will inhabit certain energy levels, these shells that we've always talked about. And left to their own devices, they'll always try and occupy the lowest possible energy shell. And if they're excited, so if you give them extra energy, they can jump from that energy level that they inhabited to a higher one. But the thing is, they'll almost immediately try to get back to their original lower energy level. And to do that, they'll have to shed that excess energy, and they do it by emitting a photon. Now, we already know that we can calculate the frequency of light by using Planck's constant, because the Planck's constant times the frequency of the photon will be equal to the energy it contains. So here, the energy shed, the difference in between the energy levels, is equal to Planck's constant times the frequency of the light you're going to get. So one more time, because that's a bit of a mouthful. So the electrons are going to shed their excess energy, and that's going to be a certain amount of energy, the difference between the two energy levels. And that energy is equal to Planck's constant times the frequency of that photon. Because different elements have different electrons in various shells, they'll emit light in particular spectra that are unique to them. So we can use this to identify them like we discussed earlier. Okay, let's have a look at mass, and we're going to introduce a new unit called a mole. So historically, hydrogen was used as kind of the benchmark for measuring atomic masses. Because it was the simplest element with just one proton and one electron, it was used as a kind of measuring stick for the other elements. So helium, for example, will be 4 times the mass of hydrogen. So the other elements were expressed as multiples of hydrogen. So oxygen would have been 16 times the mass of hydrogen. Now, for various historical convoluted reasons, carbon was chosen to be the new kind of the new measuring stick for atoms. So in particular, carbon-12, the isotope carbon-12 was chosen. And in such a way that 1/12 of a carbon-12 atom counts as one atomic mass. Okay, so why have we mentioned the mole? Okay, the mole is just a word for a certain number. So in the same sense that if I said a dozen eggs, you probably know that a dozen means 12. And similarly, I could use the word dozen for other stuff, like the dirty dozen. So you could say, I've got dozens of such and such. And similarly, you could also, it's kind of more old school slang. For 20, we use the word score. So like in the Americans, 4 and 7 years ago. So it's just a certain word used to describe a particular number. So where does the mole come in? Well, because atoms are really, really small, if we're going to be working with them, we're going to need a very big unit in order to have a decent amount to work with. So that unit is the mole. And the mole is defined as 6.02 by 10 to the 23. Now that's a really, really long number. You guys are pretty comfortable with scientific notation, thankfully, but it is a very large number. So you could have a mole of anything. You could have like a mole of mobile phones or a mole of rocks or something. But the number is so large that it only really makes sense in the context of atoms and electrons. So a mole is 6.02 by 10 to the 23 of something, and it's usually referring to atoms. So how does the mole relate to our C12 measuring stick? Well, it actually comes straight from it. So 1 mole of carbon-12 would have a mass of exactly 12 grams. Now this has very convenient ramifications for the rest of the periodic table. Particularly that 1 mole of any element, you can choose any element, and if you counted out 1 mole of those atoms, they'd have a mass equal to that element's atomic mass expressed in grams. An example kind of makes this much easier to get your head around. So for example, if I took a mole of helium, it would have a mass of 4.003 grams. If I took a mass of lead, it would have, if I took a mole of lead, it would have a mass of 207.2 grams. And if I took a mass of carbon, it would have a mass of 12.01 grams. And if you're thinking, well, that should be 12 exactly, remember that the carbon in the periodic table is the mix of all the different isotopes, whereas the carbon-12 we used as our yardstick is just that one isotope. That's where you get that slight discrepancy there. Okay, I'd like you to try the questions at the end of this chapter. Before you do, though, I'd strongly advise you just pause the video here for a moment and work through these worked examples that they've given. It'll help massively. And then have a try at exercise 30.3. And finally, we're going to have a look at the kind of the bonus mission in a moment. So this last section is kind of optional. We've already looked in detail at the Geiger-Müller tube, but just so you have an idea of how the solid state detector works, and also as a little kind of revision of semiconductors. So to build a solid state conductor, you start off with a semiconductor. And if you remember, most conductors, when you heat them, the resistance increases because the electrons have to force their way through all the kind of vibrating atoms. It becomes more difficult. With a semiconductor, because all the electrons are initially locked in covalent bonds with each other, when you heat it up, you free those electrons, and those freed electrons outweigh the increase in resistance that the temperature caused. So in effect, heating it causes its resistance to decrease. So that's a semiconductor. Okay, well if you dope a semiconductor, doping means adding in impurities, other elements in to kind of affect how the semiconductor works. So if you look at the periodic table, boron is just to the left of silicon. So silicon will be the base semiconductor. Boron's to the left, phosphorus to the right, and here I am. So boron would have 3 electrons in its outer shell, where silicon would have 4. So boron would have more of those positive holes than silicon would. And if we use phosphorus, it would have 1 extra electron. So these are called P and N type doping respectively, positive and negative. So the first one, adding boron gives you more positive holes, and adding more phosphorus gives you more of those negative electrons. If you take a silicon semiconductor and you dope one side of it with boron to give you the p-type, and you dope the other side of it with phosphorus to give you the n-type, you've now created a p-n junction. With one side, with the p-type, one side n-type. What actually happens is the positive holes on the one side from the p-type will be attracted to the n side of it. So they'll be attracted to the negative charges. And likewise, the negative charges from the n-type will be attracted into the p-type side. So what this effectively does is it creates a zone near the boundary between the p-type and the n-type where there's no charge carriers, where it's just neutral. We call this the depletion layer, where there's no free charge carriers. Okay, so how is this useful for the solid state detector? Remember, we're trying to detect ionizing radiation here. Well, if you put that PN junction in reverse bias, the positive and negative charges of the power source will cause that depletion layer to be even wider than it was before. So at this point, you've created a kind of electrical no man's land. There's no charges free to carry a charge. But if ionizing radiation arrives, it can knock free an electron from a positive hole, creating charge carriers, which then you can detect the current that passes because of it. Now remember again, this is a kind of an optional extra. If you're happy with the Geiger Muller tube, you can stick with that, but there's no harm having it for completion. Okay,